The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. Thank you for attending today's webinar by Mahr. Start to finish, surface finish measurement overview and best practices. I'm George Schuetz, your presenter, Director of Precision Gages out of Providence, Rhode Island. And if you have any questions concerning any of the material in the presentation, feel free to send me an email and I will respond to your question after the webinar by email. Let's begin. Surface finish inspection has become a normal part of the part measurement process. Mahr has a full line of surface finish products. They range from the very basic, easy-to-use portable roughness gauges to powerful roughness and profile and waviness analyzing systems. Today we're going to review the importance of surface finish, the basic process of measuring surface roughness, and then we'll take a look at the MarSurf portable surface roughness gauges that we can provide. It's very important to monitor surface finish. As dimensional tolerances have tightened, form and surface errors become more significant. Tighter tolerances are required for products for aerospace, electronics, automotive, medical, and precision manufacturing. And every surface has some function, and unless it is measured, no one will know if the product will perform as desired. So this chart shows us that since the 1940s, tolerances have tightened dramatically. But the percentage of the form and surface finish part of that dimensional tolerance has become a greater part of the tolerance. So it's more important than ever to know that the surface finish and form errors are under control. Now, why is surface finish control important? Well, there's many reasons for wanting to have a controlled surface finish. Appearance is the most obvious. That finishes affects parts reflectivity and consistency. And our top photo here shows a very reflective part and a matted part. And each one of those has a different surface finish characteristic. There's also surface function. One is adherence of coating. So if you're trying to paint a surface, too smooth a surface, the paint is not apt to stick. But if the surface is too rough, the paint might not cover it completely. And there's also surface interaction. For a sliding surface, you want to have a smoother, reduced surface finish. But maybe there's a surface finish that is more created for a specific roughness that allows for gaps for oil to sit in and help lubricate the surface. And we also want to control the surface to maximize the process. We fine-tune the speed and feed of quality of the machine tool to produce the best part with the proper surface finish. And by looking at surface finish, we can also analyze process problems, as we might see bearing failure become part of the surface that's inherent on a part, causing more roughness conditions. Now, where does surface finish come from? Well, like I was saying, basic components and elements of surface finish come from the machining or the manufacturing process. So most machining processes produce three elements of the total profile, with roughness being the most influential. So on the left here, you see we have all the components of a typical machining process. We have motors, we have pulleys and gears, bearings, a rotating spindle, a tool that's moving along a carriage, which is moving on the bed of the lathe. So each one of those puts a different component of the surface onto the part. We have the roughness from the tool itself, vibration, which shows up as waviness, long range form errors, straightness from the lathe to the bed. All those are combined to give us a total profile. And by filtering, we can select and look at each one of those components individually. Now, surface finish measurement started a long time ago with a scratch pad standard. This was the old thumbnail test where operators would scratch their thumbnail over the patch to get an idea of how rough that surface felt. And then they would try and compare their workpiece to that standard. Well, as you can imagine, that's a very human influenced measurement. But now there are some very sophisticated methods for measurement of surface finish. And those can be mostly through mechanical contact measuring systems, but rapidly in the past 5 years or so, optical surface finish measurement has become very popular and very high performance. But we'll concentrate mostly on contact surface finish. And basically there are two contact methods for surface roughness evaluation. Mahr provides both types of surface evaluation measuring instruments. These are portable roughness instruments using skidded measurement. But Mahr also provides skidless portable measuring instruments. Now you can see here with a skidded measurement, we have a drive that moves a probe along the part. And within that probe is a skid which follows the surface with the probe contact going through it. So skidded instruments measure only roughness. Waviness is filtered out by the skid following the surface, and most portable instruments use this skidded method. But Mahr does also make skidless measuring systems. These types of probes and drives have a precision, straight reference datum as a guide, which the probe follows. And just the contact itself monitors the complete profile of the part. So skidless instruments can measure roughness, waviness, and profile. Now, once we measure the profile, we want to be able to analyze the results, and those involve using different parameters. And these are standard measuring processes for determining what that roughness represents. And there are nearly 100 parameters for surface finish evaluation. And they are used for the different things we talked about, for the stability of the manufacturing process, finding the functional characteristics of the surfaces, or determining the analytical capabilities of the instruments themselves. We want some standards to tell us how good our systems are. Now, the most common parameter is R sub A or RA or roughness average. Since the roughness profile contains peaks and valleys of different heights, an averaging method is used to quantify the surface. There are very similar methods. Some are other common ones are R sub Z and R max. But roughness average, RA, is the go-to method for most analysis. It's the most common parameter specified. It gives us a good general indication of the surface. It's easiest to understand and visualize, a lot better than the old scratch standards. And it's easily quantified with a single number. You read micro inches or microns generally as the dimensional measurement. So it's very easy to understand that the R sub A equals 2 microns. Now, like I said, RA is the most commonly specified parameter, particularly in the US. Now, their confusion still exists from many years that RA was developed from RMS, but they really are not the same. Roughness average is the arithmetic average of the absolute values of the roughness profile coordinates. So RA equals arithmetic average or centerline average. RA does not equal RMS. There is another parameter called RQ, which equals RMS. And within all the ISO or the ANSI standards, there are formulas that describe how to calculate the various parameters. Now you can have very different surfaces and get the same R sub A. Now surface performance is different due to bearing contact, for example. And RA is often specified and is a valuable monitoring process for stability. But other parameters may be needed to monitor for surface function. So looking at these two drawings, you can see that they have very different characteristics, but because the peaks and the valleys are the same, you're going to get the same roughness average, but they're going to act very differently. So if this is a shaft rotating on a bearing-like surface, this is probably going to cause a lot of scratching or lots of forces on those peaks. Whereas with this type of surfaces, that contact area or that bearing surface is really spread out over the part, and this one is apt to perform better. And there are ways to identify which one of these surface characteristics we have. This one is called, one of the ways of doing that is using something called material ratio. And you can see that as we take a depth from the peak of the surface, we can calculate how much of the surface is really going to be contacting the part. So in this example, at the same cutting depth, the material ratio is very different, in fact, by a factor of 4. But in both cases, RA is the same for both surfaces. So what I'm showing here is that there are different parameters that can give us different information. And material ratio is a way of expressing that contact ratio at different cutting depths. So you can see this is a system profile done by one of Mahr machines where a sine wave was used with an example of 5 micron, and we can plot out, see for every depth, what that material ratio is. And these are just common parameters that are available in many of the machines. Now there are other different surfaces, but again can give us the same RA. But by again using different parameters, we can help to evaluate what that surface is really doing. So in this case here, R sub max can be used as a method to help evaluate some peaks that might be within the surface that can cause some problems in the function. So R max is the single highest peak to valley within the sampling length. So in these cases, the RA might be the same, but the R max is going to be dramatically different. In the rest of the world, R sub Z is a more common way of analyzing the surface, and this is measuring roughness depth. So R sub Z is the most commonly specified parameter throughout the industry in the rest of the world. RZ is the average vertical distance between the highest peak and the lowest valley in 5 sampling lengths. RZ is more sensitive than RA to changes in the surface finish because heights are examined, not the averages. There is no formal conversion between RA and RZ, The best are estimates where Z is 4 to 7 times the RA value. So this is basically a very useless comparison. So you should either measure RA or RZ. Now, where can you go wrong in surface finish gauging? Well, there's a number of different points that we must consider when we're making a surface finish measurement. The first one is not understanding the different parameters. And like I said, there's ISO standards, there's DIN standards, there's Japan standards, and you should understand which one you're going to be measuring so that if you're in a world organization, you're measuring all the parts the same way. Sometimes you can select the wrong gauge, whether it be a skidless gauge or a skidded system, what the accuracy is, those can affect the readings. Selecting the wrong cutoff, the sampling length, relying on a default cutoff, letting the machine do all the work. There are also things like not choosing the right processing filter, using an inappropriate stylus tip because tips do come in different radii, and ignoring measuring force because that can have effects on different materials. So non-adherence to the measurement conditions. Whenever we're setting up a measurement with a surface finish machine, we should understand the cutoff length, the total measuring length, and the type of tracing system. Now, there are different grades of surface finish equipment out there, and they can cause differences in readings. Systems can run an average of between 5 and 25% inherent errors. Probe tips have different styli radius of 2, 5, or 10 microns. The styling forces are different between them. The tracing speeds could be a little different, and the sampling rate can be different. So all of these can affect the result provided by the systems. Another source of errors is from the environment and the setup of the process of the measurement. There could be vibrations in the environment which are going to translate as noise on the profile. Part movement while being measured is a problem. Driving and guiding difficulties in the drive unit. If there's some problems in the drive, you can get misread readings. The wrong tracing system causing distortions or the wrong contact for that particular part. Tracing systems not aligned parallel to the test piece. There might be dirt on the surface, or you might have a worn or damaged probe tip. All of those are sources of errors within surface finish measurement. Now, how do you check the performance of a surface finish gauge? Well, standards have been developed to help define the specifications, use, results, and testing of surface finish gauges. Since surface finish consists of peaks and valleys, reference specimens contain peaks and valleys in various shapes and amplitudes that are known, measured, and certified. Thus, the calibration process verifies that the gauge reads what the patch cert says it is. Now, it's important to verify that your surface gauge is using the same probe tip radius that the test patch was certified with. Otherwise, you may be adjusting for errors within the systems, which you should not be doing. Sometimes the thought is to have a specimen close to the surface you are measuring. But I think in reality, it's better to use a specimen that uses a lot of the gauge's measuring range. Thus, you are more apt to have a more calibrated system over its own whole range, offering greater versatility. And another idea is to consider a double patch check, one full range and one fine range, as this helps to verify calibration over the full range, and it helps to identify if a tip is wearing or damaged. Now, traditionally, surface finish was done in a quality lab in the back of the manufacturing hall, for example. And there were shortcomings to this traditional method. It was reactive by nature. It was something that once the part was manufactured, you're reacting to whether it was good or bad. It helps prevent shipment of bad parts, but it does not prevent bad parts from being made, which is very expensive. And there's associated costs with labor, material handling, and inefficiencies when a part is manufactured, then brought to a surface finish gauge. Because things can happen between that time of the qualification of the part and more parts are being manufactured. Things can change with the manufacturing process. And basically, it became a go, no good, no go method of inspection. Parts are qualified as either go or no go. It's good for sorting the parts and preventing bad parts from being shipped. There's added cost in the materials and labor and rework to do that. It only recognizes deviations so severe that makes the part good or bad. There's no process control with this. And the greater the time between manufacture and inspection qualification, the greater the difficulty in finding the flaw in the manufacturing process that caused the bad part. So there's a productivity change going on with surface finish. Now we're giving measuring tools to the machine operator, which provide information for decision making right at the point of manufacture. So we're bringing portable surface finish testing equipment to the point of manufacture, which helps us find bad parts immediately. There's no lag time between manufacture and inspection. It prevents bad parts from being manufactured because we can make changes as we approach the tolerance conditions. And most of the products today are digital, providing output, which allows for data to be collected to help with that process control. Now, operators need tools that are simple to use. Operators may be experts at running their machine. They are most likely not experts on surface finish measurement. So many surface texture standards are often updated. They're hard to stay up to date. And even seasoned employees can have a tough time grasping the intricacies of surface metrology. So there's a lot involved with surface metrology, but the idea is to make it simple to put into the hands of the machinist. And Mahr offers a complete line of portable surface shop floor gauges and measuring tools. Here you can see our complete line, the PocketSurf, our PS10, the new M310, and the M400. All of these are portable surface finish measuring tools, each with their own specific characteristics that provide surface finish measurement at the point of manufacture. So let's take a look at the PocketSurf 4 for skidded roughness. The PocketSurf 4 is ideal for an entry-level application of surface measurement. It's been around for nearly 35 years. It's probably the easiest to use portable surface gauge out there with its single one-button operation. It's simplistic in that it limits selection, a bias switch of doing R sub A, RZ, or R max. It has 3 cutoff length selections, and it can be intrometric. So it's simple to understand. It has a single display unit, which gives us the result. It has output capability for data collection, and it's extra versatile with its 4-position probe, pointed out here in the picture, and it has a wide range of accessories with its probes and different stands. Now here's a little view of some of the features of the PocketSurf 4. It has it's probably, like I said, the easiest to use. One button operation starts the measurement process. It has a simple, easy to read LCD display. It's unique in its 4 pro positions, which gives it greater versatility. It can be used in any orientation, has data output, selectable traverse lengths and cutoffs. It has micro inches or micrometers for resolution, and it has 4 selectable roughness parameters. Now, recently we've updated the MarSurf 4. It's just like the original, maybe only better, the one that was built 30 years ago. It has all the same features. People know this as a standard for measuring surface roughness at the point of manufacture. Easiest to use, lots of probes and stands, basic parameters and setup. That's the standard for many of the surface finish measurement at the point of manufacture. And it can be used in the machine, or the part can be brought to the bench, and with its fixtures, it's very simple to get the part aligned to the MarSurf form. Typical applications for measuring crankshaft journals. You can see the right angle probe here. Small probes are available, and we even have a handheld V for measuring on small diameters, maybe in the machine. The next step up for our skidded product is the PS10. The PS10 is a recent entry into the market, and what's really unique about it is its large LCD display that acts very similar to a mobile phone. So everybody's familiar with the way phones work nowadays with its swiping and selection and touch screen. The PS10 tries to bring this operation to the machinist. So we have a touchscreen display. It's battery rechargeable with indications of when the battery is fully charged or not. It has a single button to start and stop the measurement. A surface probe, which allows for removal, but it also has a pickup protection device. The whole drive system is removable to put into separate fixtures. It has an integrated removable calibration standard, and it has interfaces for USB. You can store the measurements on a micro SD card, and it can use Mahr Connect for our MarCom software. So the PS10 has 31 parameter capabilities. You can see we can drag the screen down with the touchscreen to select by touching the parameters that we want. It has a removable drive unit. Normally the drive is held within the system, but you can take it out with its built-in Pro protection and then mount the drive in a stand or use the drive independently in a small bore on the machine. So the whole concept with the PS10 is a simple to operate system like a smartphone. It saves in training costs. It helps because the workpiece does not have to be aligned so critically, so there's no complex setup times. It has a very fast response. You're able to get results in seconds. Logging is performed on the device in a form of a PDF document, so there's no additional software required. You can make the PS10 act like a memory stick, plug it into your PC, and you'll see PDF forms for each of the measurements that you've made. It's really a small investment for some very accurate measuring results. Now, like I said, all the measurements that you made are put onto a memory stick, the micro SD card, and you can plug that into your PC and view those results. We have this integrated calibration standard, which is unique. You can pull it out and make a quick test to get guaranteed results anywhere. Here's an example of one of the PDF formats. You can customize the names on the forms. You can see the profile. You can use tolerances within the PS10 and classify the results through colored bar graphs here. This is all standard. There's no additional software required to produce these results. And the results can be sent directly to MarCom Software. This is Mahr's free way of collecting data and storing it to a PC. The results can be transferred into a Microsoft Excel, a text file, or into a key code location. And we can choose alternative methods for transmitting data, whether it be the function on the PS10, or we can remotely control the device to start and collect the data. So there's lots of different applications. You can use the PS10 right on the part. It has built-in V's to help align the PS10 to the part. Or you can take the drive out, mount it into this little holder here, and make this a very portable roughness measurement, for example, on this gear. There are different stands available for holding the whole drive and PS10 together, or you can mount the drive independently. Now let's talk about the latest edition, the M310 skidded roughness measuring system. The M310 is a measuring system very similar to the PS10, but with a lot more versatility. It has the same large illuminated touchscreen display. It's rotatable, scratch resistant, more indicators for status, the simple start button, removable probe, has some freely programmable function keys. But what's really important is on the back here, because it has the capability of connecting wirelessly to a Bluetooth printer, so that when you're doing the material ratio curves, you can plot those out. Sometimes, people think that, why do I need a piece of paper? Well, there's nothing better to talk about than a piece of paper which you can look at with your colleagues, talk about the process, and maybe even staple it to the work orders that are traveling with that part. So they can be a very valuable tool out on the shop floor. There's also capabilities on the back to use a USB type interface for connecting keyboards or scanners. We still have the micro SD card for saving the results. And this has a duplex capability with Mahr Connect to have external programming and setup of the device if you want to do that. So here's some of the important software features for the M310. Again, 31 parameters, very similar performance to most laboratory surface finish measuring systems. We have display and printing of the MRC and ADC curves. For tolerance monitoring, tolerance limits can be set for all selected parameters, and out of tolerance conditions are signaled on the display and on the report. So you can see color coding for things that are in or out of tolerances. And you can have specification of the cutting line C in micro inches or percentage, which makes it easier to understand your MRC curves. The USB Bluetooth printer with docking station, you can get direct printout results. You can detect the device status at a glance. These are all marked on the M310 here to know when the system is running. It uses a rechargeable battery. You can get over 1,200 measurements without having to recharge the system. And it uses a button which is made out of an oil-resistant plastic that's really meant for the shop floor and can take thousands and thousands of cycles without showing any wear. Similar hardware features to the PS10, with the probe and drive being a removable system, so it offers more flexibility. Different height adjustments were built into the device to make it easier to apply to the part. It has the integrated and removable calibration standard, and it comes with a sturdy transport case with extensive accessories. Now, what's really important with the M310 is its interfaces. It has the USB-A interface for connecting Bluetooth adapters, a Bluetooth printer, barcode scanner, etc. So rather than set up a system through the keypad, you can use barcode scanning and download all the parameters automatically. It has the micro SD slot, so that you can store all your profiles and so forth on the micro SD card, and then plug the whole system into your PC and look at those results. The micro USB interface for connection to a PC. This is important for really putting the M310 into the manufacturing process. So now you can build the drive systems into custom gauging, making it that much easier for the user to make measurements at the point of manufacture. And we have the Mahr Connect duplex interface, which allows us to take data from the M310 or store the setup parameters on the PC and download them to the M310. Along with the duplex capabilities, we have the ability to store and record the part number and gauge ID number as part of the data collection process. So really now we're tying the whole measuring process together. We know when the part was measured, we know what the results are, and we know what gauge made that measurement. A very key into tying data together. And the micro USB interface allows for remote control via ASCII commands so that we can control the system with SPC software or with machine control type parameters. So we can say start the measurement from a PC, we can record those values, calculated the parameters, and all comes as part of a standard process. Here's our typical applications where we can mount the drive into holders, use the drive remotely by itself, or even measure small parts on the holder for the drive. And here's an example of a custom engineered solution where we can build the M310 into a fixture gauge, have a tool that holds the part, aligns it properly. So it's very simple for the operator just to place the part onto the plug, press the start key, and get the results. That's going to be taken one step further. This could be an automated system where a robot loads the part onto the plug, and via the duplex control, we can now control the M310 remotely and do the whole process of measuring surface finish without a person being involved. And finally, the top end of our portable surface line is the M400, our skidless roughness and waviness and profiling measuring system. Like I said, this is a skidless system. It has motorized positioning, which is unique in the industry. And one of the most critical parts of any surface finish gauge is the probe itself. What Mahr does is incorporates two important features. We have a breakaway probe design. The probe is actually held on with magnets so that if it is accidentally bumped or brought too close to the part, the probe will break off, not damaging the system. It can be reapplied and you're ready to go make a measurement again. And also with the M400, we have the motorized positioning allows the user to position the probe above the part actually not touching it. And when the measurement process starts, the drive will move down, sense that it's touched the part, and then begin driving the probe to make its measurement. So again, less chances of damaging probes. And this is one of the most common problems with a lot of the competitive instruments. We have wireless or wired connection between the drive and the display controller. We have a built-in printer, large colored display, and all the key functions are soft keys, which makes it easier for the operator to use the system. So the M400 is a skidless roughness profiling system, very high precision probe. Provides fast probe arm change due to the magnetic breakaway probe. It takes very fast measurements, only a few seconds of settling time required because of the motorized height adjustment, and it's going to use automatic zeroing, again, taking away those critical time functions from the user. It's internationally up to date with all the most common and latest parameters per ISO, JIS, or ASME standards. And you have documentation control with the quality integrated thermal printer, printing out profile and results. Here's an example of some of the results that we can get. We can get the P profile parameters. We're doing profile, the waviness parameters, and the roughness parameters. Here's our typical applications. The probe can be used upside down. The drive can be brought to the part. It can be left on the part to make the measurements, or we can use the drive in stands or within custom fixturing to make it easier for the operator to use. So like I said, Mahr offers a complete portfolio of portable shop floor surface finish measuring tools with the PocketSurf, the PS10, the M310, and the M400. So I'd like to just summarize what we talked about today, that I think surface finish is an important parameter to measure. Production automation calls for inspection at the point of manufacture, something that needs to be done by the user, by the operator. The gauge must be powerful but very simple for the operator to use, or else they'll be fearful of it and apt not to use it. And Mahr's complete line of MarSurf mobile roughness instruments are a great solution to put portable surface finish measurement into the hands of the machine operator. So I want to thank you for your attention today and listening to this Mahr webinar start to finish. It's been a pleasure talking to you. And again, if you send me any emails, I will respond quickly to your questions.